Alright. Alright. Always less people on the second day. Going back to what we were talking about yesterday, so do not forget that today's an important day, because if you manage to understand what we're going to talk about today, you're literally talking about being 90% fluent in parametric design. You're going to be dangerous, danger zone. So today we're going to talk about data tree structures. In data tree structures, if you remember yesterday, we talked about this situation where for City of Dreams, we had to go in there and determine for any given member along its length what its situation looked like. So you had all of this, and you'd be able to say, listen, give me the perpendicular frame and let me be able to sort of see how close I am to an architectural envelope. So that's what we were talking about. We did that example where we were able to show, let's see here.
It's not started, huh?
Just started. You haven't missed much. So we started off using this one. It's very, as we said before, remember, this one saved us, let's call it a minute or two's worth of time per time. So if I'd asked you to do it by hand in CAD, it would take you 10 minutes to actually give me that picture, and now I'm pretty powerful because now for any line, you change the line, you change the position on the line, I can beat you 10 minutes at a time. But remember, the end game for this was not just to do it a couple times, it was to do it for the entire free-form section of what is a very, very complicated building. Okay, so right now I'm only analyzing it for this portion because I'm on a laptop that's not that powerful. But remember, we're talking this whole free-form zone here is what we had to do this for. We had to come up with this color plot that you're seeing there that basically would tell you how close you're getting to that envelope for the whole thing. How do you do that? So remember yesterday we said we start small, we start with a simple concept, and then you move higher. So this is generally how you will do it. You'll start by using a list. You'll go from your sketch and you'll figure out how to get that sweeper that you have on the right there. But then when you want to take that and do that a million times, you could actually have people just sit there all day long and keep going through it, bake the results, keep going through it. But this is where you start to get really, really powerful, because if you're able to take that definition now and have the computer control that definition, you're 2 levels away from where you were. So that's why this is really important. So you started with this one, and now you say, how do I get it to go from that to doing that everywhere for me automatically? We won't get into, there's a lot of discussions that happen here. This is such a great example. But what I will say is you sit down and you say, first of all, okay, I know that I need to get down to this paradigm along the length of the line every meter or so. The discussion of how often you do it is a different discussion. The important part is that you say, okay, I know that every X amount along each curve, for each curve, I will need to create one of these planes. So right away, you're talking about doing something multiple times. The first part of your script needs to be setting up these planes, which this will reside in, okay? So those of you who know Grasshopper a little bit already know that it's pretty easy to subdivide a curve, and that's going to be the basis of our starting point there. But just from an existential perspective, we know that if we were talking about it, we were just talking about it, we would know for each curve, actually I should say curve, the inputs are black. For each curve, some important words here, for each curve, we're going to have n analyzation planes, let's call them. And then for each analyzation plane, we're probably going to come up with, in general, for this project, it was 4 architectural lines. Because if you can see here, the way Zaha's envelope was, isolate one of them. Remember, it's all rule-based. There's no magic. So given the fact that Zaha's envelope was pretty predictable, okay, it's weird, it's wonderful, but it's always got 4 sides that have chamfers in the corner. We were assured by our facade contractor that the chamfers don't matter. So we knew when we broke it down, the rule for us was we have 4 analytical, or 4 architectural sides that are going to be on our analysis plane. So let me just undo that 5. Okay? So breaking it down into its nuts and bolts. For each curve, we want to look at it at n amount of analyzation planes along that to get this picture. Each one of those pictures, for each one of those pictures, you're going to have 4 lines, and then for each one of those lines, you're going to be analyzing it to see where it is. In words, we knew right away that's what this is going to involve. And the key words here are for each. This is how we know we're talking about data tree structures, because data tree structures inherently are like, for those of you who know code, looping. We know that that's going to mean it's time to loop the computer. And a lot of times this is where scripts can get very complex and things can get away from you. But luckily with data tree structures, it's very intuitive. And I think the important part is we always need to be able to break down these data trees into something that you can understand. So what they normally look like, just to put it in perspective, we talked about this a bit yesterday. If I hover over this right now, everybody see how there's these brackets there? So these brackets are actually telling us that we don't just have a list here. We have a list of a list of a list. Submatrices, some people like to call them. All right? And that can start to get away from you really quick if you're not thinking correctly in terms of if I don't associate each one of these lists to something physical, I will lose it. So, for instance, for each curve, I have it in here, the pecking order of what I care about here. I'm going to feed in curves, I'm going to feed in some architectural information, and then I'm going to feed in points. In that order, that's the way I need to be thinking. I'm doing something, the curves govern where the architectural lines are, govern where these are, okay? So right away we see the pecking order going in line of curve, then lines, then points. And a lot of times this is the way it's going to go for you. You're going to be given a bunch of information and you need to boil it down to simple, easy things, as simple as getting 2 points so that you can measure between them. Okay? Now, in terms of what you see here, that's really confusing right now. I wouldn't expect even myself, if I picked up this script and only looked at this portion of the script right now, to understand what it means to look at something and have it go 0, 0, 1. It doesn't make any sense. It's just data. It has no basis for what we're talking about. So we're going to step through the script and understand, if everybody understands exactly what we're talking about here, right? For each curve, we're going to do n analyzation planes. For each one of those analyzation planes, we're going to do an intersection, just like we did yesterday. Get this pretty picture. On each one of those analyzation planes, for each one of those analyzation planes, you're going to have 4 of these sides. And then for each one of those sides, you're going to do some sort of measuring. Okay? So a lot of levels to this. That's inherently, when you talk about these bracketed numbers, that's what it's explaining. And if you don't start on paper right now, and it takes a while to get used to this, to understand that as I'm talking, I'm thinking, when I think for each, I'm like, okay, right there's a branch. There's something that when I look at those brackets, I need to be able to recognize right away. The first one is a curve. That means that when I see in Grasshopper something here in this first indice, I should know right away. The curve is right here. The lines are right here. And usually what it ends up being is for each line, it's there. Just as a preview of what we're going to talk about here. In general, in engineering, what I've found is, so you'll have this, A, B, and then a list of 1, 2, 3, 4, and then another one. C, D, let's call it. So you'll know right away, if you frame the problem correctly, this doesn't get confusing because you know that my A is resulting to a specific curve that I put in there. My B is resulting into a specific line. So now we're talking about for one specific curve, we're talking about one specific line, and then we're going to talk about specific points that happen along that line. And you'll see this as we step through, but just as a preview, This is what the guiding principle is. Usually, if I were to come to your desk and say, show me a panel, the first thing that I'm looking at is, please bring up the panel so I can see what's going on in your data tree, so we can see what actually is it that you're dealing with. So, yeah.
There a function in Grasshopper to measure the shortest distance from a line to a surface? Because you could have defined one as a surface,
Yeah.
and then each corner of your box can be a line, and it doesn't really measure the closest distance from a line to a surface.
No.
So the function is
No.
not available.
That's the reason. So the question is why aren't you just taking in, essentially this surface, this
No, one would be a
SHS?
surface. One, 2, 3, and 4 would be surfaces,
Yeah.
and the corner of the boxes would be lines or curves, and you just have to measure the
But it
closest
was an
distance
issue,
from
okay, so this is a different question. This was an issue of not only where is the shortest, but also how much of this member is screwed up, right? So if you're only close over a span of, 500 mil or something, maybe they can work around that, the facades can work around that. But if it's the whole member, then it matters, and then there's different variations. So we knew that in general, you need it everywhere, you needed the full picture. So I think and by the way, I think to answer your real question, I don't think there is one that does exactly that. There is always a closest point to something else, but I don't necessarily know. We can check right now. Closest point to surface. Usually this is how you do it. Surface closest point, but it's to a point. So you would need to get a point on the line or figure out some sort of script your own thing. It's like math and just say, hey, what's the definition between a surface? And you might not have to do that. Does that answer your question?
Yeah.
Okay. All right, so let's talk about this script. All right, remember we talked yesterday. We referenced in the architect's geometry, Bureau-Happel geometry here, architect's geometry, and there's a parameter here called evaluation length. Currently, I've scaled it up a bit from what we used. That's this parameter here. So every 346 mil, it's a random number right now, we are taking one of these planes and we're going to start seeing what's going on there.
By considering so many points along the periphery of the box, wouldn't be the corners be the closest to the architectural thing?
We'll get to that in the end of it. It's a good question. It has to do. Let's get to the end of it. Right? There were specific reasons why everything was done. There was, like I said, there was a lot of conversations about what does it actually mean to be clashing. What is it that we're after here? 3 different parties trying to figure out the answer to this problem. So that'll be just stick with me real quick and we'll get to that. Okay, so first step in the script is, we're not going to get into this until tomorrow, but what this script does is it goes in there, inside of it, I have some components, and all it does is it says for each line that we fed in, associate it to the surfaces that are near it. We're going to talk about this tomorrow. This is a very important thing called geometric searches. Let's not jump into it now. The main point is all that's doing is taking all these lines, and for each line, it is taking and finding for it 4 adjacent surfaces. For each means we're going to have a data tree structure. And everybody take good note of here. What goes in is 116 lines, 3,000 some surfaces, lists. Do you see any brackets over there? No. But when it comes out, you see these brackets come up. And what's happened here, you can even see it visually, just for your information. Whenever you see a solid line in Grasshopper, it means you have a list. Whenever you see the dotted one, it means you have a data tree structure, which is a list of a list. So now we've actually increased complexity here. So when I look at this one, can anybody tell me in words what this number 0 means and what this number 4 means? Reverse engineer. I've been talking from here to here the whole time. What does that mean in words? Oop, what? So this 0, what does it mean?
Each section.
4. It doesn't mean, we're not on section there, remember?
Sorry,
I got like light in my face, so I can't see who's talking. Sorry.
Structural centralized.
Exactly, so that's the 0, and then the 4 is the 4 surfaces that are adjacent. So, if you are geared right now, because you've thought it out over here, and you've said, pecking order is over here, there's no confusion. You just understand, I'm on my way to doing what I did on that slider tool, but on steroids, because instead of actually having to click and put in curve, and then click and do all these different things, I'm letting the computer say, here's one curve, why don't you do it there for me? Here's another curve, why don't you do it there for me? Okay? There's no mysteriousness anymore. You've set up this system, you know you have 115 lines, those are the 115 lines. You know that Zaha's got 4 curves, that's where those are coming from. Is everybody with me on that? That's crucial, because we're going to add more complexity to it.
But the 4 things are surface, right?
They're surfaces. So if we actually look at what it says in here, if I pull up a panel, reference prep is actually surface. So all this done is just massage some information for us. Now the curves inherently are in this 0 here. We know that it's 0 is a curve actually, and we can retrieve that curve based on that number. But also now we have 4 reps associated with that curve, which is going to be important as we go forward.
So it could be a matrix of different type of data. So one curve is referring to 4, let's say surfaces.
Yeah.
Yeah.
Yep.
So it could be numbers, text, anything mixed.
Yeah,
It's
exactly.
not like coding matters in which you have to define.
Yeah, so
Float matrix.
this could be something else here. Let's say we were doing, you had a bunch of text tags out in space, and you wanted to say for each text tag, go out there and find the 4 that are closest. It would be the exact same type of thing, geometric search, which we're going to cover tomorrow. But instead of having in there 4 reps, you would have 4 text tags. Okay?
That code is written in that adjacent envelope.
I'm sorry?
So that routine is
Yeah.
written in that adjacent envelope.
Yes.
Yeah, okay.
Yes. And like I said, let's walk before we can run here, all right? And like I said before, there's some stuff going on here that's very specific to the geometry that we were given and the problem that we had. And I'm not going to get into it because actually, to be honest with you, I can't remember the exact reasons for all of it. But just remember, stuff like this line of the code right here is meant, we'll get a little bit more into this tomorrow, but to scrub out the exceptions that you might have. So for instance, we had SHS's square shapes as well as circular shapes. Those things have to be handled in a different way. Let's not get into it. Let's focus on the data trees that are going on right here. So as you go through your script now, you should be able to follow this because everything I look at, even if I just look at the data tree structures, I can see now it's changed. But it's changed, why has it changed? Well, let's see here. What's this thing doing? Split with a brep. What does that do? So you split a curve with a brep. So what have we done here? We've taken in all our curves, and we've used this bounding box that we've created from a geometry before. Okay, so in words, what this has done is this is actually taken in and it's created a bounding box. It's created the envelope of all of the surfaces that were in here, and it's used that box to clip off the curve that we had. This is, once again, a specific reason for why we did this. But should it come as any surprise that if we take a box and we clip it, or we clip a curve with it, that we get out, let's see here, we put in 116, right? And we clipped it, and what do we get out? What's the 0 index mean? In this case, no. And this is why I don't want to get too much into this one, because sometimes Grasshopper will actually give you, if you run commands, it will give you extra branches that you don't need. And in this case, you would need to look at it and you need to go, wait, everything's 0. Does that make sense? If everything's 0, could it actually be doing 4 each? No, it's just a list. And it's just telling you, I split it because, look, 2. If you take a box and you use it to split a line, you're probably at least going to get 2 pieces. There might be some in here that have 3, right? But it's either going to be 0 pieces, 1 pieces, or 2 pieces, or 3 pieces. It's not going to be 4, right? Let me skip out of this one though, because that's a little bit more than what we're going to handle today. All right, so from everything that we have here, don't worry about that. Analysis segments. If I show you a picture, this one will make more sense. So go into green mode. Always go into green mode when you're doing this stuff. Let's look at one specific bar. Analysis segments. These are planar curves. And if I turn off, can't see this one here, but okay, so our original segment, that script is basically converted, has done some operations to that line. It doesn't look any different, but programmatically it is different. It's because it's thinking. It doesn't like me right now. This is why live demonstrations never work with clients, guys. Don't ever do it. Make a video. You don't want to be in here. I mean, I'm flustered and I'm in front of friends here. If you're in front of a client and you're doing live demonstrations, it's bad news because no one likes to watch someone watch their computer. I don't care what's going on in that computer. It's not fun. There you go. Okay, let's not play with that anymore. All right, so basically, there you go. Analysis segments. We've analyzed our curves. We want, essentially, this is our input to the script. This black line here, we're going to start making analysis planes on it, right? So at some point here, we would expect to start seeing, if I go over here, perpendicular frames. I can actually change my view so you can see that better. Because we're in meters, so probably even 5 meters is too much. Let's do 1 meter planes. Bada bing. Okay, so we can see, stepping through it here, we take 116 planar curves, we convert them into perpendicular frames. Well, how do we do this? The curves, there's our 346 there, everybody see that? And for each one of those now, what's the 0, 1, 2, 3, 4, 5 mean? The curves. And why is it different now? Why is n different for each one? Give you a hint. Sorry? The distance, right? It's a division thing. Like sometimes there are longer ones, there's shorter ones. But that's okay. We're ready for that. So now we know. Okay, it seems to be working visually. I can see I got exactly what I want. And it should come as no surprise that the next thing I do gives me, if I can. Probably cut the lights now. Can we cut the lights? Yeah, it's perfect. That's perfect. We can see our 4 lines. And all that has been is what we talked about yesterday. It's an intersection tool. We've intersected 2 objects. We've got our lines. So just like that, you see that 0 index I keep asking about, that's there now. Now, we have those lines. So this lists, if we analyze the list structure, what happened here? All right, so I put in a data tree. I can see that by the line work. I put in, each one of these has 5 lines, 1 lines, 10 lines, whatever it is. Each one of these has that, and it's being intersected with one mesh. And what comes out is a different data tree structure. Does anybody understand what happened between A and X up there on the board? I'll make it really big so everybody can see this. This is important. Okay, so let's break it down. This one right here is what 0? Curve 0. This one right here is what 5?
Number of segments.
Bingo. Okay, remember that. Keep that in your head. And now, what's happened here? Remember, the first index doesn't change, right? So this is still representing curve. Now what's this one?
The number of stations.
The number of stations, but now they're in a different, now it's been segregated a little bit more, right? And now for each one of those stations, what is this? Bingo. So what does it actually mean, without even looking at the screen? What does it mean happened at curve 1, station 0? What happened? There was nothing there. for some reason Zaha's envelope got cut off before our line, right? All right, so, but the rest of them, it looked like it worked. And that's obviously something you need to deal with, but it's pretty good for what we need to do, right? These kind of exceptions to the rule, like I said, you gotta expect them because it's a computer, it doesn't know what it's doing. So you need to be able to handle them, and in this case, at least at the stage we're at right now, we just need to know basically what to do with that data. So that's that one right here. What's this one doing? Let's see. I even wrote it there. Member plane. All right, so what's this one doing? Let's practice. 0 what? Curve, right? 5, and then 5, what is it? It's the analyzation plane. And what comes out? Same type of thing, right? Why is the number 2 across the board? Let me zoom in to give you a little bit of a hint. Why is it always 2 in the list that we see here? Thickness. Things have thickness, basically. So 2 closed polylines if we looked at that, which just makes sense. Okay, now, if we go back to the board here, got a branch for curve, right? And now the lines are in a list. You can probably guess, we're going to try and make these lines now up a level and get points in the list, right? So, what we ended up doing here, going back to your question, Shibal, we had to be able to measure distance between points. As I recall, it matters which way you go because, like I said yesterday, if closest distance has to do with coming off this way like this because it's perpendicular to the member, or if it's just Euclidean, it's like this, it has a difference, right? But it all comes down to you need to break it into points first. So what we're doing here is we're actually just splitting it up to make sure that we get the quadrants of a CHS. Like I said, small little thing that you'll come across. And as you see, if that was a CHS we were looking at, you would actually see the quadrants of the CHS. It was just to make sure that we got the best points on the CHS. Let's look at the data tree though. What happened here? Now it's like, oh my God, I got 3 levels of insanity here. So I got 0, 0, 0, 1, 1, and then a list. Once again, this is kind of, it's done this split exercise between this data and this data here, and it's added a branch. Remember, if you are past 2 things in your bracket, most time in engineering, something's going wrong. Because what it means is, at least in our terms, for each curve, for each line, for each point, something else. I can hardly think of what else you would actually really need to have out of that. I mean, maybe the Cartesian coordinates or something like that, or maybe if the points had some sort of property to them, but you created the points, so really the only thing they could have is the x values. So in this case, we look at it and we can see, once again, it's a dummy first branch. You can't actually get anything out of it. That first branch is just, is not really helping us. Oh, excuse me. That first branch is still 0 to 115, and this one is still 0, 0, 1, 1, 1, 2, 2. We actually, at this point, what he's done is because we've actually split it with, you see how we have 2 things coming in here? We split it with 2 things. So it's natural that what we'll get out now has an extra 0, 1, 0, 1, 0, 1, right? So we've split it up. It should be in 4, right? Or at least maybe a bit more than that. But right now, those are split out. So what you can do in that situation is you've actually expanded your data out too much in the structure, so you trim the tree back. So now we're back to what we've been familiar with. 0, 0, 0, that's the curve. 0, 1, 2, 3, 4, that's the analyzation plane. And then here's all the curves that are now existing on that analyzation plane. Does that make sense? It's just managing how you're managing your data. All right, let me skip forward here. Actually, shatter. There we go. All right, so what we do is we take each one of those lines, right? We shatter it up. We trim our tree again because it messed up with our tree. Now we have 35 lines there. Why are we doing that? because we want a point cloud right there. This is for tomorrow. Why are we doing the point cloud? Because we're finding the closest points on the adjacent architectural lines. So let me just show it like this, right? So actually I've shown it both ways here. But what you're actually seeing is you're breaking up these lines only to, for all of them, for all, finding all the closest points over here, right? So it's dumb. It's actually checking a ton of things over here, a ton of things over here, a ton of things over here, right? But there's your points, right? So what should we see now in our data tree structure?
What's trim command used for?
Trim command is used to bring back a couple branches. So let's say right now, curve, how many, that's a bad example, you have to do some math. For curve 1, or curve 0, how many points are associated with that for the whole entire curve? Lots. Like it's like, yeah, I mean, the ones that we've created, it's 138 plus 148 plus 180 plus 142 plus 110. You can do that real quick in your head. That's how many are associated with that whole curve, because we've taken all those analyzation planes, and for each one of those analyzation planes, you have a bunch of points, right? So if you trimmed this tree back one level, what you'd actually end up with is all those points. Now, are those points on their own in a list useful to you?
No.
No. They mean almost nothing. You would, for the problem that we're solving here, it needs to be framed that way. But if you did get a third branch there that didn't mean anything to you because Grasshopper added it, or, you know, there's just times that you need to get rid of it, that's when you use trim. Does that make sense? Equally, if you want to take a list, a straight up list, and turn it into a tree, let's try that. So in what Vimal has asked us to do here, right? Let's just do a trim. I've taken that data now, it's completely on its own. Now I have 718 points associated with curve 1, completely useless data. Let's take it down 2 levels. What do you think is going to happen? What happens if we put 2 here? Right, bugs out. cannot collapse everything. I mean, you can't kill your tree, right? Go green. So we put 1 back in here. So this is an important lesson as you start off. Most of the times you're not going to jump into data trees right away. When you do run into problems that seem kind of freaky, everybody knows the trick. If I don't like this, I go over here and I go flatten. And I go back to a list, right? This is the list that we all know and love because it's really easy. That list has 157,000 different points in it. What if I wanted to make, and I'm scared to do this, but let's do it because you only live once, right? If I wanted to make this into a data tree, into something that had 157,000 branches, I would graft it. I'm not going to do that because actually I'm a little bit, I think it'll crash my computer and then our lesson will be over. But in general, if I wanted to graft something, you come over here, you graft it, it brings things up a level, right? So it's flatten and graft and trim are how you kind of control the branches of your tree. Let's see here, I think there's also, somewhere in here, there's a, I don't use it personally, but you might like it. It's the data map. I'll find it later. There's a tool that actually helps you visualize the data trees, but to me that's a little bit like, it's really, for Bureau Hopping people, we shouldn't need it. So, what have we done here? We've gone from having the points in this format, where'd it go? All right, so zeros are the curves. Second ones are the planes here. And now we have same thing, but now something's changed. And what's changed is it's the curves, it's the planes, and now it's a bunch of points, right? So there's our pecking order right here. That's what we were expecting to see at the beginning. These numbers, these letters, these variables here tell us what we're on, and then these ends up being points. So that's what we wanted in the first place. And then, as you guys can see here, if I turn off green mode, the cool part now is everything's in a nice little box for me to come in there and play the simple game, which we're going to talk about tomorrow, which is geometric searches, which is all those blue lines that I just drew here, all of them. or all these blue dots. So we said, okay, create all these, then from those, create all these, right? So it's a closest point type of thing. What's the closest point on this line from this one? And then it's a distance, right? So it's which one of these has the smallest distance between here and here. So you can see there's a bunch of discretization going on here, just so we can get down to these points, just so we can get down to distances, just so we can take the max of them and then throw, as you can see here, throw a dimension line on there like that. But the whole thing, and even when we get down to the bottom here, you know, you see these limits that I have over here. The same color scheme applies in both, right? So if you have a distance that's less than 99 mil, you are in big trouble, right? If you have one that's greater than 138.9, the architect's telling you that's all right, right? And the important part is now, you can see, if I turn off the architectural data, right? Now it's a tool that's easily checkable, and that's the important part. Easily checkable. We see a lot of people who jump right into making Excel sheets that they don't understand, blah, blah, blah. None of this should be that way. So the computer now is spitting out to me and it's telling me all along this line right here, I think that it's clashing. It's within somewhere along the line of 109 to 119 millimeters. Now, if this was Excel and the computer told you, you made this fancy script to tell me, hey, where do I have clashes? If it tells you you have a clash here, how do you check it? It's like, no way, right? I mean, Excel can't check it. You can't check it in Excel. You'd have to go back into Rhino and try and do old school sort of cutting plane, measuring, that kind of thing. Well, luckily for us, we started on a different foot, right? So we can always come back in later. Let's see here, turn on London center lines. And use our first tool to sort of verify the second tool. So because it's a lower order tool. And sure enough, if I start playing with this now, it gives me the nice image. I can see the values right there. I trust the values. And you know, okay, these lines that we're seeing here, these dots, they're true. And if the architect comes in and changes the threshold, I should be able to see the colors changing, right? And then them actually going away, getting worse, 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 that kind of thing. So in summary, that's all possible because we started with the picture, and we got the one tool. And then we said we want to put that picture on steroids. How do we do it? And we sat down right away and said, take that algorithm and apply it here, 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 for each. Whenever you're sitting down at the beginning and saying, how many times do I want to apply this? And you say, well, it would be nice if for each one of these I got this, and then it breaks down. This conversation of the closest point thing, remember yesterday we were talking, you might come up with this, you'll come up with this first. And then once you get back to this picture for so many times, you'll have to say, oh, how do I actually start playing this game? Actually, and then it starts to be, okay, let's see here. And then we'll get another level of for each going on, and then we'll have the analyzation points and distances that come naturally. It is not necessarily easy. In a class like this, you'll never learn it. It literally is the best. The reason I go to this example is because it's intuitive, and the most important thing you can do is keep it in a way that the branches, the actual interface that you're looking at when you're stepping through. So when you look at this, what can be a very weird looking syntax right here, the zeros, the ones, all the brackets and stuff, if you already have in your mind what those mean physically, then you will be okay. If you don't, this is where you'll throw parametric stuff down. The same stuff applies to Dynamo. It's all in the interest of making looping very easy. Remember before, like I said, we had before the slider, right, and we had the curve. And we had this component, right, that generated that, right? Without this component, with this component, this slider right here saved me 10 minutes at a time. This business right here, plus another little slider, the 346 mil, put into that, saved me 10 minutes of time for, what do we have, even just 116 members right there per every 346. We're talking, you just take 2 steps forward instead of just 1. That's why it's important. So that's all I got for this one. Any questions?
I highly recommend taking a look at Nick Sensky's video and trying it for this one particularly, because this is where you'll go from kind of, oh, hey, look, ooh, ah, to actually something that's really, really powerful. I'm here all week, remember, so come on by, come give me a chat if you have questions on things, and hope you enjoyed data tree structures.
How did you put that little window there? How
Little
to create
window.
that view, which can be,
See if I can get our screen back. So,
that seems a very nice visualization there.
yeah, you're talking this one, right?
Yeah.
Well, that's kind of the nice thing about Grasshopper is it kind of lets you, like if you were making your own software program, you'd have to think, okay, I want the user, you'd have to design it in mind. It'd be nice if the user had 2 windows and you'd have to come up with 2 viewer windows. Grasshopper takes care of all of this for you because first of all, Rhino already has the ability for you to create windows, so you don't have to worry about programming how to create a window. And the second thing is given that you know you can create the windows right away, it's just about making sure that you can transmit what is geometry here. Essentially, it's here to over here. I think we talked about this yesterday, where that's just a component that transforms one plane to another over here. That's in there.
And then you assign it to that particular window.
Exactly, just copying it. And I would also say it's a good point, the vector operations, you know, if you're doing force transformations or any sort of things that involve vector transformations, do not go and start pulling out stiffness matrices and stuff like that. Don't start trying to script matrices and stuff like that in Grasshopper. Do it here, or in Excel. Do it here. They already have it programmed in there. All the calculus 3 stuff that you might need for the vectors going from here to here, it's already in there. So don't mess around with it. This is how all of City of Dreams was done using this. And it's extremely effective. So in Jamal's question, it's literally a vector transformation from this random 3D plane down to the origin XY plane. And that's how you get this beautiful little tool. And tomorrow we're going to cover another tool that's somewhat like this in terms of the question you've asked. It's essentially, it regards almost how do you sit down and say, what is the tool I'm creating? It's almost like thinking like a software engineer.
How you did the color coding?
The color coding is a very nice thing. So anytime you see colors like this, you probably are looking at someone who's in red mode, okay? Because green mode will only show green, obviously. But red mode, if you're on red mode, you see everything here. If I right-click it, its preview is on. Now it's on, right? I turned it off. The only things that previews are on are these things. And what are they? They're custom previews, if I can show it. So all it says is, give me some geometry and give me a color, and I will allow you to show that in that color. So that's at the end of your script. Remember, when you're working through your script, you're probably in green mode, but then at the end, you know, my end game was to show, in this instance, points. So I knew my points are all going to get funneled to some sort of coloring scheme, but those would be the only things that get shown.
I
And
think in the input tab you can find that color,
swatch.
yeah, where
This-
you can give the numbers and specify. Basically, you can define your scale. Yeah.
This is where you really start to get brownie points from clients and stuff, because you can make some really, really pretty pictures. With all, even if it's bad stuff like this, like it still looks pretty. So keep that in mind. It's a really useful tool. All right. All right. Thanks for your attention.
Thanks.